Hello, everyone. Today we're going to talk about something really fascinating. It's a concept that is secretly, running behind the scenes of so many things we use every day, from weather forecasts to the keyboard on your phone. It's called a Markov chain. Now, I know the name sounds a bit heavy, but trust me, by the end of our little chat today, you'll see it's a beautifully simple idea.
So here's our roadmap. We'll start with this simple concept of a memoryless world. Then we'll get a proper definition for Markov chains. After that, we'll look at what makes them tick, something called the transition matrix, and we'll even do a calculation together, don't worry. Then we'll see how to predict the future, and finally, we'll tie it all together and see why any of this really matters.
All right, let's jump right in. Before we even think about writing down any formulas or any maths, let's just try to get a feel for the main idea. Let's build some intuition first.
So let me ask you a question. How do we normally think about the future? We usually look at the past, isn't it? For example, if you're trying to guess the weather tomorrow, you might think, well, it's been raining for the past 3 days, so you'd probably guess it'll rain tomorrow too. We use history. But what if that's not the only way? What if the past doesn't matter?
This is the big idea. This is the secret sauce behind Markov chains. Imagine a world, a system, where whatever happens next depends only on where you are right now. Not how you got here, not what happened yesterday or the day before. All that history is forgotten. The only thing that matters is the present moment. The system basically has amnesia.
Okay, so we have this intuitive feel for it now, right? This idea of a system with no memory. Now let's put a little bit of formal structure around this. Let's give it a proper name and a definition. And don't you worry, we will go very slowly, step by step.
All right, don't let this equation on the screen scare you. I promise it's just a fancy way of writing down exactly what we just said. You see this P? That just stands for probability. This little vertical line here, it just means given that. So the left side is asking, what is the probability of the future given the entire past? And the equation just says, well, that's exactly equal to the probability of the future given only the present. See? All this extra history, poof, it just disappears. It doesn't matter.
And have a look at this picture. This makes it so clear, doesn't it? You see the states, x1, x2, x3, and you see the arrows. Notice how the arrow from x1 only goes to x2, and the arrow to x3 only comes from x2. There's no big arrow that jumps all the way from x1 to x3, and that's the whole point. The next step only depends on the step right before it. A very simple, very beautiful picture of what we're talking about.
And there you have it. That's it. Any system, any process that follows this special memoryless rule, this Markov property, we give it a special name. We call it a Markov chain. Simple as that. Okay, so we get the idea. But, so what? How do we actually use this to calculate anything or make predictions? Well, for that, we need to look under the hood. We need to find the engine that drives this whole thing. And here it is. This is our engine. It's called the transition matrix, and we usually just call it T. Really, you should think of this matrix as the complete rulebook for our system. It contains every single probability from moving from any one state to any other state. Want to know the chance of going from state A to state B? Just look it up in the rulebook. It's all there.
Now, of course, every journey has to have a starting point, right? You can't start the engine if you don't know where the car is. And that's what this is, the initial state vector. We call it mu0. It's just a list of numbers that tells us the probability of being in each state right at the beginning, at time 0. So back to our railway station example. This vector might tell us there's a 20% chance you start at the chai stall, a 50% chance at the samosa stall, and so on.
Okay, one more small thing. Just a little assumption to make our lives easier for now. We'll assume our system is time homogeneous. Oh, it sounds very complicated, I know, but all it means is that the rules don't change. The probability of moving from the chai stall to the book stall is the same today as it is tomorrow and the day after. Our rule book, our matrix T, stays the same. It's a simplification, but a very powerful one.
All right, enough talk. Let's get our hands dirty. We have the concept, we have the tools. Now let's actually calculate something. Let's see how these pieces, the starting vector and the rulebook, work together to predict what happens next. Okay, look closely at the screen now. We have everything we need right here. We have our system with 3 states. We know where we are starting. That's our mu0 vector at the bottom, which says there's a 0.3 chance of starting in state 1, 0.4 in state 2, and so on. And we have our rulebook, the transition matrix, which is just all those probabilities written on the arrows. Our job is to find the probabilities for the very next step.
So how do we do it? Well, it's just one beautiful, simple multiplication. We take our starting vector and we multiply it by our rule book, the matrix T. Let's walk through it together for just one of the states, say state 2. How can we end up in state 2? Well, we could have started in state 1 and moved to 2, or started in 2 and stayed in 2, or started in 3 and moved to 2. We just calculate the probability of each of those paths happening and add them all up. And we do that for all the states to get our new vector for the next step.
And voila! After we do the multiplication, this is what we get. Our new vector, mu1, is 0.3, 0.45, 0.25. So what does that mean? It means that after one time step, there is now a 30% chance of being in state 1, a 45% chance of being in state 2, and a 25% chance of being in state 3. See how the probabilities have changed? They've shifted. We've just used math to predict the future.
Okay, that is fantastic for predicting one step ahead. But who cares about just one step, right? What if I want to know what happens 10 steps from now, or 100 steps? Surely I don't have to do that multiplication 100 times. Oh, no. There is a much, much smarter way.
The answer is this elegant, simple little formula. It says that the probability distribution at any step k in the future is just your starting vector multiplied by the transition matrix T raised to the power of k. That little k up there, it's like a time machine. It lets us jump as far into the future as we want in a single calculation.
Just think about it. It's so logical. You want to look one step into the future? You multiply by t to the power of 1. You want to see 2 steps into the future? You multiply by t squared. 100 steps? You guessed it. You just multiply your start vector by t to the power of 100. So simple, so powerful.
So, okay, I can almost hear what you're thinking. You're saying, Professor, this is some very nice math, but why should I care? When am I ever going to use this? And you know what? That is the best question of all. Let's connect this abstract idea to the real world you live in every single day. The truth is, you use Markov chains all the time without even knowing it. When you do a Google search, the PageRank algorithm that decides which result to show you first, that's a massive Markov chain. You know when your phone suggests the next word you might want to type? How does it know? It's a Markov chain. It's predicting the next word based only on the current word. They are used in finance to model stock prices, in weather forecasting. They are, quite literally, everywhere.
So my hope today is that I've given you a new pair of glasses, a new lens to see the world. And I want to leave you with a challenge. As you go about your day, your week, look for them. Look for these memoryless systems. Maybe it's the sequence of songs on a shuffled playlist. Maybe it's the traffic lights on your way to work. What in your life behaves like a Markov chain? Give it some thought. The answer might just surprise you.